I want to continue on the time sync part. Hopefully, we'll wrap this thing up today. So we started looking at time synchronization when it moves onto a network, and I had kind of talked about a few of the things. But the main idea out here is that in many settings, we basically have a network of sensors and whatnot, and they need to synchronize among each other, or oftentimes they need to coordinate within the network. So kind of on an ad hoc basis. So essentially having all of them synchronized back to an NTP server or something like that tends to be kind of an overkill, because they need to synchronize kind of on demand, perhaps not all the time, and perhaps subsets of them. So this problem has been approached sort of over time by many researchers, and turns out it falls into a broader category of problems where in a network I have measurements between pairs of nodes about some physical quantity. In this case, it happens to be clock offset. And then we need to assign a value to every node so that our measurements are satisfied. So for example, in think of as some network. Each edge represents a clock offset. And the problem here is one of assigning, so each one of these represent a delta between the clocks, and let's say we pick some node as a reference, let's say we pick node 11 as a reference. Then our problem can be formulated as one of finding an offset value for each one of the other nodes such that the measurements are met as close as possible. So for example, due to noise and all, we may often end up with the challenge that if between two nodes I take different paths, then the offsets may add up to different values. So for example, between 4 and 1, I have several possible paths. I can go 4 to 1 directly, so I have a direct measurement. I can go 4, I can add the offset between 4 and 2 and 2 and 1, so that gives me another estimate of offset between 4 and 1, likewise 4, 3, 1, or 4, 3, 2, 1. So there are 4 possible paths out here. And in general, because of measurement noise, they will not lead to the same result. So the optimization problem that you end up with is find an offset for each one of the node such that once you have an estimate, once you have a solution, then if you go back and then say, okay, whatever value I assign to 1 and 4, my estimate should give me a result which is as close as possible in some, let's say, a least square sense to the different measurements. So usually what is done is I have a bunch of measurements, I make an estimate, and then I minimize using some optimization algorithm the error function. And the error function in this case is what my estimate is predicting for a particular path versus what the actual offsets along the path are. Now, if you think about it, this problem. Yes.
So just sorry to clarify, you mean, for example, for a path from 4 to 1, that you check every single possible path, and then you would.
Right. So between 4 to 1, I have, in this case, there are 4 paths, right? 4 unique things. So I can again 4 2 3, 4 3 1, 4 1, and 4 3 2 1. I guess other one is actually 5, right? And also 4 2 3 1. Okay, so there are 5 paths. Okay.
Right.
So each one of them is giving me an estimate independently, an estimate of the offset between 4 and 1. Okay. Of course, my solution is going to be just one particular value. I'm going to assign something to 4, something to 1. And then I can take the error between this estimate and each one of these 5 cases and do a joint optimization of that. Okay, you could there are other things you could do. You can weight them, so you can say, look, longer the path, I'm going to give lesser the weight and things like that. But broadly, that becomes kind of the idea.
So does this break down then as you have many nodes? Is the time to calculate every single path?
So other things you can do is you can focus on shorter paths. You can filter away the longer ones. So there are many different ways you can kind of approach this thing. The interesting thing is that I'm talking here about time, but exactly the same problem happens in location also. You can replace these measurements by distance of somehow time of flight or radio signal strength. So they're giving me a distance, and instead of clock offsets, my goal is to find the position. Okay, exactly the same optimization framework. So lots of theoretical work in, again, last 10 years or so, people have looked at different approaches for doing it. Now, solving this problem in a centralized manner is hard, as in you just have to think. It's harder yet if you want to do this thing within the network, okay, in a distributed manner. Interestingly, some of the approaches for solving this have been based around modeling this thing as a circuit with these distances representing resistances, or mechanically they represent springs. And what you're trying to find is the assignment which gives me the least energy in a potential energy space. Okay, so essentially kind of some sort of a relaxation method can be applied. So fair bit of sort of work from signal processing optimization side of the world. The other approach, I guess the first generation of approaches, had gone more along the lines of identifying the path, identifying the shortest path or path which are close to being short, and then taking an estimate between them. That worked well for time, but doesn't work well for positioning, because in position we are not simply assigning one variable, we are trying to embed it in a 2D or a 3D space. Even more interestingly, this problem also occurs in other domains. So for example, some of the solutions have also come from the world of molecular chemistry, where these represent atoms, the nodes, and the edges represent bond energies, and you're trying to find the shape of the molecule. Kind of there's a fair bit of work across the different domains which have happened, but essentially at the end of the day, you're trying to find an embedding of the nodes in some physical space with some notion of an energy, and trying to find a least cost solution of some form. So in ad hoc setting, this becomes a thing, and then usually you need, in case of back to our time story, you need some sort of a reference. So might be one of these nodes might be a reference, perhaps it is a GPS, and everything else can kind of refer to that if you do need a global time. But you can also use this thing for doing subgroup level localization. How these measurements are done could be a variety of ways, and what those measurements represent. So we talked about sender receiver and receiver receiver. So one approach could be a receiver receiver kind of thing. So one node or some beacon blasts out a packet, and then a whole bunch of, simultaneously we get a whole bunch of measurements. Or we could have a bunch of pairwise things. Recently, some work out of my group, a couple of students, what they've done is the same measurements. If you think about time of flight, they actually give you information about clock offset and distance simultaneously, because we cannot separate them out. This is a point I had made last time, which is whether my clocks are offset or whether my propagation delay is higher is something that you cannot decouple just from these messages. You can use them either way. So now what has begun to happen is that our ability to measure time has become good enough that time of flight based localization, as in measuring distance between two radios by measuring the time of flight, has become viable. Lots of people are using it. The issue then appears is that if my clocks are offset, then what are they providing me? Now, usually when we talk about finding distance, precisely because clocks are not localized, the way distance measurement is done is via round trip. So basically what node A will do is, node A will send a packet to 6, 6 will bounce it back to 5, and with the round trip, and assuming that, again, symmetry of propagation, 5 will basically say, okay, the round trip type was something, and it will have either an assumption that 6 was a perfect zero time reflector, or we know the delays at 6, and then 5 can estimate the distance. So again, let's say I want to find what distance between me and one of you. So what I do is I send out a packet, you bounce it back, and there are ways of bouncing it back within the analog domain with essentially close to zero delay. So when I get the packet back, I measure the departure time, arrival time, just according to my clock, and then divide it by 2, and I have an estimate of the range. Okay. Now, the problem with this thing that appears is measuring time is very hard. because I imagine doing it on a cheap node, and if we are doing across this room, we are talking about measuring nanoseconds, and error is directly going to be proportional to the resolution. So the trick now, at the same time, if you go to like Home Depot and all, you find those laser gizmos, which basically give you a millimeter level distance measurement to the wall on the other side. Anyone knows how they work? Right? You've seen these things, right? So you are trying to get the room dimension. You have a device. You press a button. A laser beam shoots, comes back, and they give you the distance down to millimeters. What are they doing?
Is it just the intensity of the light that's reflected back?
Nope. Nope. It's laser, firstly, so you're not going to see. I mean, intensity is going to be very, very crude. So,
Time delay?
huh?
Time delay?
So time delay could be done, but I would need an insanely because remember, if I'm doing millimeter accuracy, so then my clock has to be something which is able to discriminate millimeter level time of flight. Millimeter level time of flight is going to be in picoseconds. So that isn't happening in that $40 device, right? So any thoughts on how these things work or might work? Is there some other aspect of a waveform which relates to time? Phase. Okay, so now problem with phase is that you always have a 2 lambda ambiguity, right? Or rather lambda ambiguity. Okay, so how do we deal with that? So the point Manoj is making is that the time round trip is going to manifest itself as a phase difference between the waveform I'm sending out and the waveform I'm getting in. But the only thing is distance over 2 lambda. Okay, so I can measure round trip. I can measure distance modulo 2 lambda, but that doesn't take me that far. So what else?
Staggered pulses.
Staggered in what sense?
Using the pulses.
Now, why would that help? Each one of them will still give me modulo 2 lambda, so that's not going to help me. So the trick that these things use is you vary the lambda, okay? And it turns out if you vary the lambda, then you are going to get measurements at different lambda points. They are going to give you a slope, and the slope of the line basically helps you disambiguate. Okay, so by changing the frequency, sweeping the frequency, you could kind of do that. So they get away with that. But now what we are seeing are devices which literally do measure time of flight because they have a very high speed clock. Internally they multiply. They use ultra wideband radios and all, and they get down to 10, 15 centimeters kind of accuracies. So I guess time and location now are intermingled. I'm making a measurement, and that measurement is telling me something coupled about the clock offset in the distance. Okay, and now you can imagine that I have a whole bunch of these measurements, and they are all coupled with both location, or rather the distance, as well as time. If I'm worried about location, then clearly this set of measurements out here is not sufficient unless I know that all my nodes are in a 2D plane, because I need to form sufficient measurements so that I have a body which is rigid in 3 dimensions. But by making a bunch of these measurements, it turns out you can do a simultaneous locationing and clock offset estimation. So that's also possible now. Okay, so back to the time story. So assuming nodes are in a situation where we don't have to worry about asymmetries of propagation delays and things like that, then essentially we can solve an optimization problem and end up with the clock offsets. As you might expect, despite all of this, there will be an error propagation. So the more hops you go, there will be a buildup of the errors, and lots of people have studied that. Interestingly, so one of the groups out of UC Santa Barbara, what they have also shown is the impact of what the topology of the network, the role it plays. So again, intuitively, what it boils down to is the following. If my sensors, my sensor in this case being the message exchange that we do to estimate the clock offset, if they have a certain amount of noise, then a direct measurement versus a measurement where I add up the offsets along different paths, I have to weigh them differently because if you think of the noise being Gaussian, then essentially if I'm adding them up, then my variance along the longer path is going to differ from the variance along the single path, and therefore you do a weighted least square type of an optimization, which if the noise is Gaussian. So topology of the network or the logical topology of the network. What I mean by that is the route that the packet takes in a networking sense as opposed to what is in principle feasible. So direct measurement is always better, but direct measurement also leads to the possibility that you may have some sort of to faraway node, some sort of a multipath might be happening. So preferably kind of something shorter. Now, what all of that has also led to in recent times is that could we exploit time synchronization for could we do something to reduce this error propagation that we're talking about? So again, as the packets are propagating, there is an error propagation building up, and is there a way we can kind of deal with that? So some work in the past 4 or 5 years have focused on that particular issue. In particular, what has begun to happen is, and this is some sort of interesting work which has come out of group in Italy, University of Michigan, a couple of places, which have basically sought to combine medium access control protocols, or specifically flooding of packets with time synchronization. So kind of the idea becomes that we combine time synchronization requires sending packets out. So as we kind of saw that FTSP and these kind of things, they basically send a beacon out. The beacon propagates through hops and disseminates the time information. So what these guys have been doing is they basically try to see, is there a way we can use the fact that we anyway need to flood packets in the network for disseminating routing information and things like that. Could we tie them together and do a very energy efficient flooding and at the same time achieve time synchronization precisely? So without and kind of limit the error buildup. So think about how flooding typically happens. So usually some node, let's say, needs to disseminate a command or a routing instruction or something like that. So what it will do is it will send out a packet. It will be heard by everyone who is within one hop. And then all those one hop neighbors are then going to use some sort of a policy to further disseminate it. So usually what is done is based upon some scheme, you'll make sure that they stagger their retransmissions so that they don't collide. And then the second hop nodes will hear that, and then the third hop and fourth hop. So gradually these things disseminate, and protocols like FTSP, which are doing time sync, they also have to do the same thing, because otherwise your time sync packets will end up colliding with each other. So what typically ends up happening in these systems then is that at every hop when the nodes are transmitting, some way of staggering them, probabilistically staggering them. So for example, a very common strategy is that the initiator sent out a packet, everyone heard it, then the node with the lowest ID will transmit soonest or probabilistically soonest. Node with a higher ID will transmit probabilistically the latest. So they kind of select a random number based upon what their ID is, what their respective IDs are, and then select a delay based upon that. So FTSP would have to do the same thing. Now what happens in this case is, if we focus, for example, in this diagram on, let's say, a pair of nodes, these two. So what would happen is, initiator sends out a packet, it needs to be flooded. This guy, the top guy will transmit, let's say, first. A little bit later, this guy will transmit the same packet. So I have multiple waves of these packets which are being retransmitted, because the one hop neighbors are going to transmit that time sync packet or flooding packet multiple times. So there are multiple waves that will propagate through the network, and that adds to increased delay, but it also begins to affect your time sync characteristics, because some packets are going to take a longer time. They are going to be seeing a longer queuing delay along the path, and therefore that will affect the time sync. So what has begun to happen in these kind of schemes is that they leverage time sync to make the whole process a single pass process, eliminate collision. So we need flooding for time sync, but we leverage time sync to make flooding more efficient. That's basically what these schemes are trying to do. And the way they work is the following. Let's imagine two nodes have a packet, are sending a packet each. Then normally we say that, okay, these packets have to be separated out in time. Because if they are not, then at the receiver they can collide. But if the packets are perfectly identical, then we can let the packets collide, and the receiver will still be able to decode them. Okay, so kind of the idea being, if I'm saying a word and you are saying a word, and if a different word, then we collide in time if there is a if our transmissions overlap fully or partially even. But if we are saying exactly the same word with exactly the same analog waveform and we transmit them at exactly the same time, then there won't be any problem, because the two transmissions will perfectly overlap and the receiver would be able to see them. So the trick now becomes that could we arrange for, let's say, these first hop neighbors to retransmit that packet that they are supposed to be flooding in a manner which is synchronized right down to the bit level and is absolutely identical. If we are able to pull that off, then all I need is these guys to agree in time, which our time synchronization is providing, and then they can do a single transmission. So after one packet delay, they will all transmit in synchrony an identical packet, and even if their transmissions are heard, if a second hop node, if it hears transmission from more than one of them, they will still overlap perfectly in time and still be able to decipher it. Now, there's certain assumptions out here. We also have to assume that the difference in propagation delay across the path is sufficiently small, smaller than the bit size or the symbol size on the air. And the other thing is that synchronization is good enough so that, again, any synchronization error doesn't cause any problem as well. So this notion that that collision of packets is a lost cause is something which is in recent times is in wireless communication in a variety of ways has been exploited. That is not necessarily true. You can let the packets overlap and you can still make use of that information that is getting. There are much more advanced ways of doing it, but in this case, just imagine I'm flooding an identical packet. It's perfectly overlapped in time, and therefore I can still discriminate them. So that's the basic approach. We at a very high level, what these schemes do is they enter periodically into a flooding phase. So this will happen as frequently as we need to sync. And kind of the idea is that hopefully I have a packet to send anyway for network maintenance purposes and all, so I can make beneficial use of this opportunity to send packets out, like some sort of a command information to all the nodes and stuff like that. But even if not, to maintain time sync, I'm going to be doing it. So every so often, there's a packet going out, being flooded to the network, and what we're doing is we're going to do the synchronous transmission. So we are going to assume that the nodes are time synced, and because they are time synced, they can therefore do these transmissions in a perfectly synchronous manner. So in this plot, T1 and T2 are going to send out their packets perfectly synchronized, or kind of synchronized to an extent that any collision is not going to have any problematic effect. The receiver is going to see as if there was a single transmission. What that boils down to at the end of the day is that our synchronization between T1 and T2 has to be within certain delta. This original work, the radios they were using were these Zigbee or 802.15.4 radios, and it turns out that a synchronization of half a microsecond works out there. Okay, so if in their particular case, the receiver will receive packets with a very high probability if the delta is 0.5 microsecond. What that means is that if we can somehow make sure T1 and T2 are sending out their packet right down to that symbol level from the radio, just no more than half a microsecond apart. What that means is that their knowledge of time should be within half a microsecond, and any delays in the software which is sending the packet out and on should also keep it bounded. Okay, so not easy if you are using kind of if you are doing this. Trying to have two applications running on two different nodes do something half a microsecond apart is not something which is easily doable because of OS delays and all. So you have to make the whole thing very predictable all the way down. So imagine the task being, I give you two nodes and I basically say, you have to toggle their pin no more than half a microsecond apart. That's essentially the task. And you have to optimize not just time sync, you have to also optimize your code so that all those delays are met. These guys were working with smaller microcontrollers, so you have a much better lower level control, so they can pull it off, but not always necessarily kind of doable. From a higher level. So basic idea then becomes, I have a network, the initiator sends out a packet, it is heard by everyone. This packet could be either a packet meant solely for time synchronization because I have nothing else to do, or maybe it was carrying some routing information or something like that, and I'm using it for dual purpose. Now, all the one-hop neighbors have heard it, and at that stage, in a normal flooding case, each one of these would have done some coordination to separate out their subsequent retransmission. But in this scheme, they all transmit together. So kind of essentially the point becomes either do things totally staggered or do things perfectly synchronized. The in-between part is a problem. So in this case, perfectly synchronized, the thing sort of propagates, and in a single pass, with minimal delay, you basically end up getting the packet through. And by the way, simultaneously, you're also time sync because you're also carrying information about the timestamps and stuff like that. So, so that's the basic kind of idea. This is just a time diagram of the same thing that is happening. There are some other nuances to worry about out here, which is when hop number I transmits a packet, not only are the packets being heard by the next hop, but they're also being heard by the previous hop. So anytime you have a multi-hop network like this, your throughput goes down. So in the sense that the initiator has to wait for a certain amount of time before it can do another packet transmission because it has to let this wave sort of go through entirely. The challenge in this work, a big part of their paper was really about making sure that we are able to achieve this half a microsecond kind of thing. So we have to start execution at the same time, therefore meaning that they have to be time synced. We have to make sure that any variations in the hardware and all, as well as the execution time has to be deterministic. So variations in hardware could even be because the crystal oscillators on the two nodes don't have a perfectly identical frequency, for example. So a lot of low-level optimization they did, making use of special signals from the radios and all. But if you can pull this off, then flooding becomes very efficient. Usually flooding, like I said, is a problematic aspect in networking, and you also get a very good time sync as part of it, with no error buildup also, or error buildup being significantly sort of slowed down in the process. So anyway, this work, what these guys achieved was 0.4 microsecond in a 8-hop network, which is pretty amazing relative to kind of the schemes which were not using it, because there we were seeing this kind of a number on a per hop basis. So what this is showing is that the rate of growth of error is slowed down significantly as well, because we are just doing a much more rapid kind of thing. So there are basically two issues with this kind of approach. One is that being able to implement this kind of a very deterministic delay thing and all is not something that you can easily do if you don't have low-level control over the radio. And the second thing is that you have to set aside a certain time where the entire network is just doing flooding, nothing else. Okay, so your flooding packets are given the special treatment. So every so often the network just goes into this mode where we just do a flooding pass and then come back. Not something which sort of is how standard protocols and all kind of operate. But if you could make that happen, it kind of works out rather beautifully. So to pull this thing off, a whole bunch of sort of issues that need to be handled. Okay, you have to also model the drift of clocks, because the last time you synced to the next time when you are syncing, your clock has drifted with respect to your neighbors. So you have to model that. That in turn is affected by how often the gap between two successive flooding periods. So there is a coupling between broadcast, the rate at which you are sending out these packets, the clock characteristics, your ability to provide that deterministic execution. All those kind of things come into play. But around 2010 through 2012-13, there was a flood of papers around this concept. I only presented kind of the first or second paper, but there have been subsequent sort of work around this idea, which essentially probably at this stage represent the best idea in terms of what you can do in a multi-hop kind of a setting. Just flood this thing out as rapidly as possible. And now when you have the offsets, now you can go and use one of those schemes which stitch them together. Okay, so if you want to find the offset between two paths between two nodes, but if you are able to achieve 0.4 microsecond up to 8 hops, that pretty much means that you're already pretty good. 0.4 microsecond is a terrific number to achieve, and over a 8 hop network for sure. And most networks you are going to see with 8 hops, you can go, let's say 150 meters or so, 100 meters or so. That's a fairly large footprint, even in relative to our buildings and all. So it's good for a lot of indoor settings. Okay, so other distributed synchronization approaches. So it turns out that the issue of synchronizing in a network, while it gained a lot of prominence in recent years because of wireless sensor networks and all, at the theoretical level, in biology and physics and CS theory, has been studied quite a bit for a variety of reasons, as I'll kind of point out. And there are certain approaches that have emerged around those ideas over time. So one very common way in computer science, there is a class of algorithms, a problem which is referred to as the consensus problem. So consensus problem basically says that could we all reach an agreement? Okay, on so let's imagine the following, that we all are going to have a variable, and we want to assign a common value to all of that is, each one of us should agree that there's a common value we are going to assign to this. And if you can do that, then in effect I have achieved, if you can do that for the clock phase, then we have achieved synchrony of phase. Okay, that is, we can basically say, could we agree that the time at which I'm going to toggle the pin is the same as the time at which you are going to toggle the pin on your node. Okay, so if we can agree on that, then that's a form of time sync or phase synchronization. So consensus problem. So the way these things have worked, intuitively, the idea is the following: I'm going to advertise my value, and so is everyone going to. And I'm going to listen to your values. You're going to listen to everyone else's value. And the approach, one type of techniques, the way they work is they basically say, I'm going to move the value of my variable to be the average of whatever I've heard. Okay, so let's say, again, we want to agree that we all will have a common value for some variable x. So I select some random value, you select some random value, let's send some range, and then we all say, okay, let's just advertise it. Okay, so we send out a broadcast packet, you send out broadcast packet. I'm hearing broadcast packets now from different people, and what I do is basically I keep taking the average and move myself towards the average. Now, of course, since I'm moving my value towards the average, and so is everyone, so there's going to be some dynamics in the system, but idea is eventually everyone converges. Okay, so that's one way you can imagine consensus being achieved. But there are many other consensus algorithms which sort of exist. But this kind of hear your neighbors and move to what the consensus of the crowd is. Yeah.
Didn't we run into a problem with a similar thing when we were talking about scheduling algorithms where sometimes the clock would move backwards and that would cause issues?
You would, which is why these things are not time synchronization, they're just phase synchronization. Okay. Now, it turns out this idea is very common in biology. Okay. So in 90s, there was a fair bit of interest in biology and physics on synchronization emerging in natural systems spontaneously. And a classical example which is cited a lot is fireflies in certain part of the world. And what happens is, so I'm sure everyone knows fireflies, these are little insects which glow, okay? And it turns out that if there is a colony of fireflies, after a short while, they glow and whatever, they light up and go dark in synchrony, okay? And sort of biologists and all, and always, so after this phenomenon was reported, then kind of like what is happening? Like, I mean, are they exchanging are they communicating somehow? What is going on? But essentially, after a short while, they enter synchrony. It turns out the same kind of stuff we see a lot. There are synchronization of neuron spiking, which we see in brains. There are all sort of other synchronous behaviors that exist in networked systems. All sort of biological phenomenon enter into synchrony. So there's obviously there has to be some subtle message exchange which is happening, not necessarily in explicit message information, but some physical, chemical, biological information gets exchanged. So in 90s, there was a fair bit of effort at trying to come up with a model for these phenomena. And then later on, some computer scientists picked up that to create time synchronization protocols around these biological models. So sort of at the end of it, the model which sort of emerged and was successful in predicting a lot of observed phenomena is what is called as pulse-coupled integrate and fire model. Okay, so the idea is the following: that we are able to observe, a node is able to observe the firing of another node. Okay, so firing of a neuron, the glow of a firefly, and so forth. So what's happening is that at each node there is a free running oscillator. Okay, and what normally it does is it integrates, and when so there's some variable, and we integrate that with the passage of time, and when it reaches a certain value, we fire, and then we reset and we repeat the process. So if I had an isolated node, that's all it will be doing repeatedly. It will basically integrate the variable with time as measured by its local clock, and when the variable reached a certain threshold, it will fire, emit a light signal, whatever, and reset this variable, and then the whole process goes again and again. Now, if there was no information exchange with any other party, then essentially you would have a oscillator which is running freely with a certain frequency, and therefore the firing would be according to a certain frequency. Now, what the phenomenon we are interested in is that I have a bunch of such free running oscillators, and these oscillators have differences in frequency and also differences in phase. So if they were to not be able to communicate, and if I were to observe their signals, I will see different frequencies, and I'll also see that because the frequencies are different, then also the phases would differ. Okay, so I'll not see any synchrony. But because of what is called as pulse coupling, we see that after a short while, these pulses, the one which are emitted when the integral hits a particular threshold, they end up getting synchronized. So some mathematician, physicists, and all, they kind of developed some models, some idealized models to explain this phenomenon, and then over time, over the next 10 years or so, so by like 2010s or so, a lot of these things were sort of assumptions were relaxed and all, and they showed that in most networks, this kind of phenomenon would be seen. So the relevance to our problem is the following, that if I'm in a purely ad hoc setting and what I want to achieve is coordinated action, okay, of some sort, then this is perfect, because what it's really saying is that I want a shared notion of passage of time, that is, the frequency should be aligned, and also phases should be aligned, that is, when node A fires, then node B also fires. So it's achieving clock and frequency and phase synchrony, but it is not achieving time synchrony. So the way pulse coupling is posited to work is the following. Each node has some internal variable, state variable, x of t. A pulse is emitted whenever x of t reaches 1, and what the node does is it evolves x of t according to some dx over dt is some function of x. Okay, so there is some local process which basically grows x, and when x reaches 1, then pulse is fired, or whatever, LED glows or whatever, and x is made to be 0, and the whole process restarts. So without coupling, each state equation is periodic with some frequency. Hopefully, the variation in frequency isn't that much, but the phase is certainly different. Now, what pulse coupling does is the following. If a neighbor fires, then the state variable is updated. So the idea is that I have a notion of time, and I'm periodically doing something. But I see you are doing something, the same firing of action, you are doing it a little before I did. So next time around, I'm going to speed up a little bit. Or if I see that you are doing it a little bit later, I'm going to slow down a little bit. And every node does that. So the idea is we are observing our neighbors, and we are trying to keep up with them. If they are faster than us, we speed up. If they are if they fired a bit before us, so we next time around we fire a little bit quickly. And if we see that they fired a little bit later than I, then I slow down next fire a little bit. So what's happening now is that every time the neighboring node fires, then I guess this should be x of j or something like that. No, x of I. So basically, every time I observe a neighbor firing, I apply a correction to x of I. So x of I, the ith node, instead of just doing this integrate and fire, is now also creating jumps in this x of I. Okay, so move up, move down. So you can think of that, this is a special version of that average of my neighbor. Okay, now every time a neighbor does something, I react to it. And what that therefore leads to is that the overall equation of the system is that xi of t is growing according to whatever my original oscillation function was, but now is also getting a correction according to when the neighbors fire, and of course neighbors may be firing at specific instances of time. So when the jump happens depends upon when the neighbors fire. So it's a pretty complicated coupled differential equation with some nasty kind of Kronecker delta functions sitting out there. It turns out, though, that these guys, starting with that original work back in 1990, they showed that under certain conditions on what this function is, the f looks like, what they showed was that for almost all states, starting states, we achieve synchrony. Okay, so the result was under certain idealized conditions, namely assumptions on the function and the connectivity of the network. So the initial assumption in these systems was everyone can observe everyone. Okay, so I have a network, everyone is a fully connected, it's a clique, so everyone can observe everyone. And then basically what they showed was that for most starting states, we reach synchrony. Okay. Subsequently, these assumptions were relaxed. So, what should be the nature of network connectivity? What kind of functions we can accommodate? All of these things kind of over time got relaxed. And so, for example, in 2004, there's a paper in one of the sensor networking conferences. What they showed was that there is a condition that you can define on the topology of the network. Okay, so you can, if the topology of the network satisfies certain condition, in a sense placing some constraint on how the information can flow, then also things converge. Not going to go into that. The main thing I want to show is the following: that essentially, across a wide variety of network topologies and under fairly relaxed conditions, the scheme works out nice. So when you start out, oscillator phases are all over the map, and then very rapidly they converge. I guess I stopped tracking this field in the past few years, but the last work that I had seen was a group out of Harvard. They had basically created a medium access control protocol around this idea, basically, and they showed some pretty good results around it. So there are different, so you see the phases converging, or like in this particular case, they start out taking some actions, and initially the actions are synchronized, and then later towards the latter part the actions are synchronized. So synchrony emerges just as a natural outcome of this sort of observe thy neighbor and try to keep up with the neighbor kind of approach. And there's a rich mathematical sort of structure behind it and all, which it's important to note though what it doesn't achieve. It is not saying that you have the same time. What it is saying is that you have the same clock, and the clocks are in sync, as in they're pulsing together. But it may be certainly possible that one node thinks it is 3 p.m. and another node thinks it's 5 p.m. Okay, that is a separate problem. So this is achieving phase and frequency synchrony, but it's not achieving time synchrony. Okay, so at the end, so we've seen several different ways time synchronization can be done, both between pair of nodes. So we had sender receiver, receiver receiver, as well as the network scale. Kind of just find a route, treat the whole problem as a optimization problem of some form. This kind of a flooding based approach, and then this kind of synchronization as a consensus problem. And there are many, there are others also. Synchronization is sort of important problem in many scientific disciplines, so people kind of study them in a variety of ways. Back to our network of embedded systems and all, what it kind of boils down to is probably not going to be a single answer. For many cases, NTP is perfectly fine. For other cases, PTP is a technology. For yet other cases, maybe you just can have GPS disciplining your clock. And for some other systems, like really tiny sensors in a building, making synchronous measurements and all, one of these kind of techniques is going to be the answer, because those are very low power nodes, and burdening them with GPSs and all is not going to happen, and they don't even speak NTP and all, so you don't have that kind of access. So you're sitting in kind of some sort of a multi-dimensional space, and some sort of a compromise across energy, quality, and whatnot needs to happen. What has also begun to happen in now is the following: that it used to be this phenomenon of time sync was something somewhat esoteric, in the sense that only specialized systems had to worry about it and all. But over time, what has begun to happen is that a lot of applications, even on our normal devices, more general purpose computing devices, are becoming time aware kind of applications. Okay. Firstly, our phones and all are engaging in sensing kind of activities quite a bit. There are oftentimes we deploy sensors, collect readings from different sensors, and then we want to kind of detect a phenomenon across them. So each one of them is independently maintaining time. One of the leading causes of problems in ICU instruments in hospitals is that there are no that they oftentimes capture things which are time-stamped very differently, and they don't even know which is happening. So this kind of timing error is more stupidity than lack of time synchronization, but timing error is very prevalent in those kind of systems. Can you think of something in your what kind of things we do on our phones where you think time plays a very critical role, which sort of begin to fall into the category of time critical type applications? And I'm not referring to low level functions. Yeah, there is GPS on your phone and it does wireless communication. Those certainly need time. More at the application level, can you think of stuff where time would play a critical role? Time, at least at a level which is not easily handleable by kind of just standard timing services. So I guess none of you do gaming, okay? Because the example which cellular companies cite the most is multiplayer gaming over cellular networks. Okay, so there are two issues that emerge out there. One is one of sheer latency to the server. Okay, so you need to keep that extremely bounded, and the other one is if being able to disambiguate who made the move first on a planetary scale, multi-party gaming. Okay. The other one in more general purpose setting that I mentioned a couple of lectures ago was the whole financial industry. The trades taking place, and they are taking place at sub-microsecond level granularity, and when things go bad, then forensic analysis of what happened first, what happened later. Okay, so those kind of issues. So what we have begun to see is the need that time of a level of precision and accuracy and whatnot, or resolution, that many relatively general purpose applications are expecting, which wasn't the case some years ago. So we are seeing so Linux in recent
So like the call we make, the internet access to mobile, that is also like time synchronized, right? Every 5 milliseconds, the time division duplexing will be working on it.
every five the call as into the cellular phone. Yeah. So the voice communication has historically been a very synchronous network. In fact, the whole telephone system in this country, the classical telephone system, and therefore all over the planet, is a completely time synchronized system. Okay. We have moved away from that in recent years towards voice over IP kind of things and all, because synchrony comes at a cost. Synchrony comes at the cost of over provisioning, time slots which are not being used. But you're right that time synchronization, cellular spectrum is sliced in time, and base stations use very high accuracy crystals. Okay, but that kind of stuff has been around because one of the best ways of making efficient use of spectrum, if my traffic cooperates, has always been to time synchronize. And therefore, telephone system and then the cellular system, these are all highly, highly time synchronized. What has begun to change also is that applications like gaming and the financial industry and all, they are suddenly demanding time synchronization at a planetary scale with accuracies which were previously sort of not there. Database transactions is another one. Okay, I mean Google and all, they run these massively distributed databases across different data centers, and again you want to kind of synchronize the timestamps across transactions which are happening at different places. I make a request. Once it might go to data center 1, the next time it might go to a data center 2, and then they need to reconcile. So again, things have to be time synced, and the rate at which these things are happening, you again need synchronization or knowledge of time, which is microsecond, sub-microsecond kind of regime and all. So what has begun to happen in recent years is a fair bit of effort towards supporting time at a better level than it used to be, even in a general purpose setting. I'm going to pick on this topic on Thursday. I'm going to let you guys go earlier today because one of my students will also sort of complement some of this topic. But what I've seen now, what has emerged in recent times, real-time has now become a standard part of Linux. So real-time scheduling, real-time threads and all exist as part of the standard Linux release. People are adopting, there's even real-time Android, there are real-time versions of languages like Go and all. So what all of that kind of is showing is that there's a lot of interest in all or need of applications running on relatively general purpose platforms, but at the same time aiming for tighter control over the time. Even on platforms like Raspberry Pi and all, there are specialized boards you can buy to achieve better timing, things like that. So there's a fair bit of effort that sort of is going into that. I think over as we go along, more and more of our applications are falling into that category. I see the proposal I'm writing on drones, and I was just looking around the kind of apps which have emerged on Android and iPhone around drones and all. That would be another example where time plays a critical role because they're trying to do control from apps on phones onto these devices and also time-aware apps of various form are essentially sort of becoming more and more pervasive. So I'm going to stop here earlier today, and on Thursday, basically plan is to go into, it would be a shorter lecture again, but looking at it from the perspective of what's happening in the Linux time stack and those kind of issues. Basically. So the other thing is I never came around to actually handing out the topics for the talk, which I intend to do today, and then basically we just want to schedule them with the final 3 lectures. I will also give out a non-programming homework just so that we cover all the concepts that I have talked about, but it would be kind of a simpler conceptual homework basically. Okay, so this way you will at least be tested on the lectures, but primarily we'll go with the projects. If there are any issues on the project side, since we are now just 3 weeks away from the end, so make sure to talk to me. If there is anyone waiting for any other piece of hardware or anything like that, then it's very important. If there's anything which is stopping you from progressing, then come in, talk with me. Okay? So see you on Thursday.